Let's try a couple more examples. I'm not going to go over all of them in this video. I might not even go over all of them in class. So I think that you can do it. I just think that we can spend our time a little bit more wisely because I think you guys are getting this pretty well. All right, so here's a slope field for example 8. For x is less than 0, so that means any x value less than 0, we're talking about over here, all solutions are decreasing. And that wouldn't be true because if we start a solution over here, it's going to be increasing. All right, so that one is not true. So I'm going to cross it off, and any answer with 1, I'm also going to cross off. All solutions level off near the x-axis. Okay, and that is true because as you come along here, it's kind of leveling off. As you come along here, it's leveling off. All right, so that is true. For y is greater than 0, so now we're talking this piece, all solutions are increasing, and that is also true. So we're left with this. All right, so example 9. Oh. The slope field for this differential equation, oh man, glad we don't have to draw that. We'll have vertical segments when what? So remember, vertical segments, that is an undefined slope. So that's when our denominator equals 0. So we need to figure out when this is going to equal 0. All right, solve that for y. So y equals negative 2x. So it's when our denominator equals 0 and the numerator doesn't. So I see that our only option here would be letter B. All right, next example 10. If y of 0 is greater than 0, all right, if y is 0 is greater than 0, so we're talking about somewhere in this portion, then the limit as x approaches infinity of y of x is about 0. That's not true here, because as the x's get bigger, the y's get bigger. So that's not true. If our y value is between negative 2 and 0, so we're talking about this portion, then the limit as x approaches infinity is negative 2. And all of these seem to have the graph approaching negative 2, no matter where you draw that. All right, so that one would be true. And lastly, we're talking about this portion. If y of 0 is less than negative 2, then the limit as x approaches infinity is 0. So if you start here, it goes towards 0. If you start here, it goes towards, is it going towards x equals 0, though? I mean, y equals 0. So it's not, right? It's going towards y equals negative 2. That's where it's leveling off. So that's also not true, so it looks like it's going to be 2 only. All right, so this may be the last one that I'm going to do with you here, and then we'll talk about the other ones if you want. So sketch a slope field. This is something that you can do, but I notice anytime x or y is 0, I'm going to get a slope of 0. So I'm going to go ahead and put all of those in. All right, so now let's see, if x is 1 and y is 1, we get 1/2, so that's not going to be too steep, and then that's a little too steep for 1/2. So something like that. If one of them is 2 and the other one's 1, our slope is going to be 1. And so this is something that you can do. I'm just going to try to fill them in. If I made one wrong, oh well, you can tell me later, okay? Same thing down here. So I'm guessing they would go something like this. If I'm wrong, that's okay. Tell me. Ugh. Come on. All right. So something like this, sure. All right, let f be the function that satisfies the given differential equation. Write an equation for the tangent line to the curve. So I'm going to do part B over here. Through the point 1, 1. So at 1, 1, my slope is 1/2. So my tangent line is going to be y equals 1 for my y value plus 1/2 times x minus 1. All right. So that wasn't too bad. Then use your tangent line equation to estimate the value of f of 1.2. So I'm going to say f of 1.2 can be approximated by y of 1.2, all right, which would equal 1 plus 1/2 times 1.2 minus 1. All right, so that's going to be 1 plus 1/2 times 0.2. So that's about 1.1. All right, that wasn't too bad. Part C, find a particular solution for this equation. So that means I'm going to have to separate my variables here. So I'm going to go ahead, I'll rewrite it up here. dy dx equals x y over 2. All right, I have to bring my y over here. And I need to bring anything with x over here. So this is one where I can separate, and we're going to do this more in the next section. So we get ln of y equals, so that would be 1/4 x squared plus c. There's my general solution, but now I'm going to plug in the point. So at 1, 1, ln of 1 is 0. Okay, and then I get 1/4 plus c. So c equals negative 1/4. Great. And then I have ln of y equals 1/4 x squared minus 1/4. And last, I'm going to solve that for y. Y equals e to that 1/4 x squared minus. There we go. Great. That's a 4 there. And use your solution to find f of 1.2, which we can approximate by y of 1.2. Actually, this is equals, right? Because we found an exact solution. And plug that in, and you get about 1.116. Okay. So now, D, compare your solution. So I'm going to do that up here. Let's see. We'll say the estimate was an underestimate. There we go, underestimate. And the reason why is because, look, it's less. There we go. And then use your slope field to explain why. So we're talking about an equation here. If we drew our particular solution, right, it's always going to be concave up. So we could say that, right? We'll say because the slope field, or we could call it the solution curve, would be concave up. All right, there we go. And so that would tell us, since it's concave up, our tangent line would lie under the curve, so it'd be an underestimate. All right, so there are a couple more problems. We have example 12, which was actually on one of the exams. We also have example 13, which is another good problem, and example 14. So we may go over those in class. I'm not going to take the time in the video to go over them, however. All right, have a great day.